this morning. As I was introduced, today I'm going to be talking to you about some recent advances in artificial intelligence and machine learning. So what do you think about when you think about artificial intelligence or AI? When a lot of people picture AI, they think robots. Maybe they think like a personal companion robot. Maybe they even picture, unfortunately, a Terminator robot. But this is actually pretty unrealistic. What is modern AI, really? Well, as many of you probably know, you constantly interact with AI systems in your daily life already. So anytime you use voice recognition, that's AI. Anytime you use machine translation, which I've been relying on a lot this trip, that's AI. Anytime you use systems that recommend content to you, we know that AI is enabling autonomous driving, and there's actually a lot of really interesting new developments with AI that could potentially be really beneficial for people. And these are things that people might not know about. So it turns out that we can actually recognize tumors in medical scans with better accuracy than trained doctors, all thanks to AI. So this could be really, really useful. But how does all of these systems work? The answer is through something called machine learning. So all of those systems that I just listed to you use this technology called machine learning. So what is machine learning? A good definition is algorithms that are able to learn from data without being explicitly pre-programmed. And usually this involves some form of pattern recognition and inference. So when you're doing machine learning, you can do different things. You can do things like cluster your data to be able to find different related groups of data. Often what you're doing is making predictions. So if I want to be able to tell whether a medical scan has a tumor in it or not, what I'm doing is called supervised learning. I take a bunch of data that's been labeled as tumor or not tumor, and I train an algorithm to learn this decision boundary between the data that has the cancer and the data that doesn't. The third type of machine learning that I'm going to talk about today is called reinforcement learning. And in reinforcement learning, it's a little bit more active. What you have in this type of learning is you have an AI agent that's actually taking actions in the world and observing the reward that it gets back in response. And then it tries to learn to optimize for this reward. So all of these technologies are really interesting and cool, but actually they've all existed for many years, like 50 years. So why is it that we've seen so much rapid progress in AI recently? Why is everything suddenly starting to work so well? Why did voice recognition suddenly get so good? Well, if you ask me, I would say it's all because of deep learning. So what do I mean by deep learning? How many people here have heard of deep learning before? Awesome. Okay. So for those of you that haven't, I'll give you a brief introduction. What is deep learning? It's actually really simple. The basic idea is you take a very simple neural net, or even just a regression function, which works by saying, okay, I have some input data X. That data has some features. I'm going to multiply those features by a set of weights, sum that up, and get some number. And then I'm going to use that number to make a decision. So maybe that number says, yes, here's some cancer, or no, here there isn't. So this is a very simple idea. What is deep learning? It's basically just scaling up this idea, adding many hidden layers, and then learning how to train that effectively, how to optimize it effectively so it actually works. So all of the progress in deep learning recently, most of the progress, is about understanding how to get these algorithms to actually learn effectively when you have so much more capacity. So why is it that people are suddenly so excited about deep learning? Well, I would put this all back to something that happened in 2012 with this computer vision competition called ImageNet. So basically, the goal of this competition is to get a computer to be able to look at an image and understand what's in that image. So recognize that this image contains a bird. So before 2012, people in computer vision had spent their whole careers, like 30 years, developing better and better techniques to do things like edge detection and contrast enhancement to be able to try to recognize what's in these images. But then in 2012, this deep learning team came with some well-optimized neural network and basically just absolutely crushed this competition. It was twice as good as the next best entry. So every other entry is competing for tenths of a % improvement. This deep learning model comes and is just amazing at this task. And since then, people have gotten really excited about deep learning for computer vision. And now we can do all kinds of things, like scene labeling. So we can get a neural network to look at an image and tell exactly which pixels are ground, sky, and car. And this turns out to be incredibly useful for enabling autonomous driving. So that's pretty cool. But it gets even cooler. We can actually get a neural network to look at an image now and know that that's a picture of a woman throwing a frisbee in a park, or that that's a picture of a group of people sitting on a boat in the water. So this is really incredible. Suddenly, AI seems to really be able to understand these computer vision tasks. So this got me and many other researchers very, very excited. So a lot of people started getting very enthusiastic about deep learning, and it turns out that conference attendance at these machine learning conferences doubled every year and is growing exponentially. So basically, there's a lot of hype around this field. Everyone's getting really excited. They're all getting on board this hype train. But there's some question as to whether all of this hype is deserved. Is it really as good as people say it is? Does it really deserve all of this enthusiasm? People get especially a little bit skeptical because there's been a lot of investment in AI recently as well. Suddenly, companies are getting really interested in machine learning, and they're putting a lot of money behind it. So you might say that there's way too much hype. There's no brakes on this hype train. How do we stop it? So the point of the talk today is I'd like to get you guys on board this hype train, because I think it is deserved, and I think we should be enthusiastic about these models. So I'm going to tell you a little bit more about how deep learning works, and then I'm going to go into some projects that I've done spanning a lot of different areas, creative AI, medical machine learning, and finally a project on multi-agent reinforcement learning. So I'll start with talking about why does deep learning work so well? Well, I would argue it's because of representation learning. So what do I mean by representation? What is a representation? Well, it turns out that when you take some data, like for example, this really cute picture of a cat, and you feed it into a neural network, and you look at the activations of the weights and the neurons in a given layer, that activation of neurons in a layer is called a representation. So you can think of all those numbers, all the activations of those neurons, as a vector in a big n-dimensional space. So this vector is the representation. And it turns out that deep neural networks are really good at learning useful and meaningful representations. So for example, if I train a deep neural network on just a ton of text, I just train it on all the text I can find on the internet, then I can look at the representations for different words, and I can actually do some math with those representations. So let's say that I let f of x be the representation, the encoding of the neural network for a given word. Then I can do stuff like this. I can take the representation for the word king, subtract the representation for man, add in the representation for woman, and any idea what I get? Queen, exactly, exactly. So isn't that cool? It seems like this neural network, just by consuming a bunch of text, has learned some conceptual understanding of the relationship between these words. So this representation seems really meaningful. And we can even do this with geography. If I take the representation for Santiago, I subtract out Chile, and I add in Greece, what do you think I get? Athens, exactly, exactly. So this neural network has actually learned something about geography just by consuming a ton of text. So this is really exciting. And you can actually do this kind of math in image space as well. We can do this with the representations of images with a network that's been trained on images of human faces. So if I take the representation of a smiling woman, subtract out just a regular woman, and add in a man, guess what I'm going to get? A smiling man, exactly. So isn't that cool? And what's really neat about this man is not a real man. He's never existed in the world. This is just completely generated by this neural network. And it doesn't work if you just do this with the raw pixels directly. So if I just add up all those images, I get a blurry mess. So it's actually the representation that gives us this power to combine these concepts flexibly. So that's what's really cool. And I'll show one more example of that. I can take a man with glasses, subtract out what makes him a man, add in a woman, and I get a totally new woman with glasses. And again, not a real woman. She doesn't live in the world. This is just made up by this neural network. and you can't do it just by adding up the pixels. So we think representation learning is really cool. But what has it actually got us? What have we been able to do with this representation learning? So I'll give you a few examples, just a couple. People are really excited about generative models. So a generative model is I want to be able to generate data that looks like real data. So just like we saw that image of a fake person, I want to be able to do that effectively. One of the coolest models that has come out recently is called a generative adversarial network, or a GAN. So the way this model works is actually really cool. It has two parts. The first is a generator network. And that generator is trying to generate a fake piece of data. So it tries to make a picture that looks like a real face. And then the second network, the discriminator, tries to be able to tell if that picture is a picture of a real face or it's a picture from the generator. And that's where the training data comes in. The discriminator tries to tell, is this real data or is it fake? Now what's really cool is if the discriminator is able to detect that this is a fake image made by the generator, the way in which it was able to detect that is actually used to train the generator. So to be more technical, the gradients from the discriminator are directly back-propagated into the generator to help it learn to improve. So this actually turns out to be really good at generating samples. Now, in 2015, when this first came out, people were very excited about this because this neural network was able to generate these fake images that look sort of like bedrooms. That kind of looks like it might be a bedroom. It's not a bedroom that I would want to live in because I'm pretty sure the walls are melting into the floor in some of those rooms, but it looks like something, so people got really excited. But what's really cool is how fast this has progressed. In only 2 years, in 2017, these are fake images now. So this image of a face here, that's not a real person. This is just something that this deep neural network was able to generate. But look how realistic it looks. So if you look at that man in the corner there, he actually looks like a real person. If you look really closely, his teeth are a little bit messed up. But still, that's pretty good for a totally fake face. And then just this year, Big GAN came out and absolutely blew everyone's mind because it was able to generate fake images of almost anything. So again, this is not a real dog. This is just a dog invented by this network. So people are getting very excited about this. The other big area that people are excited about is called deep reinforcement learning. So as I mentioned before, reinforcement learning is this idea where you have an AI agent that's more directly interacting with the world. So it takes an action, and then it observes how well did that action go. It looks at the reward it got from the environment for taking that action, and then it tries to optimize for its total expected future reward. So people are getting excited about deep reinforcement learning because once we put deep neural networks on it, there were a number of really interesting successes. So for example, we see that neural networks are able to play Atari. And I had a video here, but it looks like, sorry. Oh, yeah. OK. I'll get back on the Wi-Fi. I'm so sorry, guys. OK. Oh. So yeah, here we go. So just thanks to deep learning, this neural network was finally able to actually make some progress in reinforcement learning. And you can see that it's learned to play this video game. It's not perfect, but it's doing pretty well. And then the other big success that you might have heard of is AlphaGo. So who here has heard of AlphaGo? OK. So what's going on with AlphaGo? Go, or sometimes what it's called is Chinese chess, is a very, very complicated game. And there are actually more states in the game of Go than there are atoms in the universe, if you can believe that. It's a very complicated game. It's impossible to just brute force it with raw calculation. But thanks to deep learning, deep reinforcement learning specifically, DeepMind was able to train an AI that could beat one of the world's best players at Go. So this is Lee Sedol, and actually the algorithm was able to play Go better than he was. So people got very excited about this. And since then, there's been some other successes in DeepRL, particularly with robotics. So you can see that, OpenAI recently trained this hand to be able to manipulate objects using DeepRL. And it actually can do it in a way that's very human-like. The movements that it uses turns out to be very human-like. People got excited about that. But the thing I'm actually most excited about is this idea of DeepRL for data center cooling. So a data center houses all of the servers that are actually used to run algorithms like deep learning models. And to be able to run the data center efficiently, you need to keep it cool. But there's like a ton of different fans and switches and air conditioning controls that need to be run to keep the data center running efficiently. Turns out, if you let a deep neural network run the data center, it can actually reduce the energy consumption of the data center by over 10%. So I think this is really exciting, not only because basically the deep neural network brain is sort of controlling the body that houses the deep neural network. So it seems like we've built some kind of AI hindbrain, which I think is really cool. But that's a bit of a stretch. The other thing that's really cool is this is just really beneficial for climate change and sustainability. If we can get all of our buildings running 10% more efficient, we're going to save a lot of energy. So that's pretty exciting. So there's been some pretty big successes in DeepRL. OK, so that's hopefully gotten you a bit on board the hype train. Now I'm going to get into the details of a couple more projects. The first project I want to talk about is a project in creative AI. So this is something I did in collaboration with the Magenta team at Google AI. And what we're trying to do here is show that we can improve a deep learning model by making it socially aware of feedback from humans. So I'm going to argue to you that making an AI agent socially aware will make it smarter. So how many people in the audience have ever had this experience where you're talking to Alexa, you ask her for something, she completely mishears you, and she does the wrong thing? It's like, yeah, come on. I'm surprised more hands didn't go up. Come on. Alexa can be pretty frustrating, right? Or Siri. So chances are, if you've had this experience, the next time that you respond to Alexa, you might respond with frustration. There might be a little bit of an edge in your voice, and you're like, Alexa, why did you do that, right? So wouldn't it be great if Alexa could pick up on that cue and learn she did the wrong thing? Why can't she improve from that? But currently, people aren't looking at this. People aren't looking at making AI systems detect your emotional and social signals in order to improve. So that's what this project is about. What we want to do is we want to generate samples from a deep learning model and show them to people. And then we want to use the person's social response to tell if the model did a good thing. And we're going to focus on facial expression detection in this project because facial expression detection is just a little bit more mature and accurate as an emotion recognition technology. We're pretty good at accurately detecting what face you're making, but it's still hard to do other things like tone of voice. So the idea here is to detect facial expression response and then improve the model using this feedback. So we had a big question with this, though. Are there any deep learning models that people might actually smile at, that might actually cause people to make faces? Well, we settled on this one. It's called SketchRNN. So what this does is it draws human-like sketches of things like regular objects, animals, and it draws them in sequence in kind of an animated pattern. So we thought maybe there's a chance this could make people smile, especially if it draws something cute. So what we ended up doing is we built a system to collect data that will show someone a sketch, and it'll observe their facial expression response. And if it sees that they're frowning and they don't like the sketch, it will say, I think you disapprove of my sketch. I'm not going to draw like that again. But if they smile at the sketch, then it'll say, OK, good. I'm going to try to draw more like this. And then to train this, we use a model that actually combines a GAN, which I talked about earlier, with a variational autoencoder. So you don't need to know exactly what a VAE is, but you do need to know that it's a model that's especially designed to get a really good representation. That's my favorite word, representation learning, right? So using that really good representation, what we can do is we can learn which parts of the representation space actually correspond to sketches that are more likely to make people smile and less likely to make people frown. So the way we do that is pretty simple. We get a bunch of representation vectors, which we're calling Z. We code them into sketches, and then we look at whether people smile and frown at those sketches. Then we train a model that says, given a Z, what do I expect the facial expressions to be? So this is the first part of our GAN model, the discriminator. It says, how good are the facial expressions for a representation vector? And then finally, in the third step, we train our generator. And the generator here is just going to give us better representation vectors that we think are going to decode into sketches that are going to make people smile more and frown less. So did this actually work? Well, I'll just show you guys a few examples to try and make my case. This is how the model used to draw cats before we did anything. So you can see it sometimes draws a nice looking cat, but some of them look a little weird, right? So if we just train with a few examples of people reacting with their face to these sketches, the model actually learns to draw a significantly different type of cat. Now it's drawing these big fat cats with little smiles and whiskers. So clearly it has learned something about what it thinks will make people smile. And it's done that with very little data. So whether you think drawing cuter cats is an amazing scientific achievement, I don't know. But let me give you one more example to try and make the case that this can work. This is the SketchRNN model trying to draw rhinoceroses. And it turns out it's just really bad at this. Like, sometimes it draws something that looks like a rhinoceros, but I don't know, whatever that is, it's not a rhinoceros, right? If you just train with a few examples of people reacting to the sketches, you get a model that pretty consistently draws something that looks like a real rhinoceros. So it's actually able to improve the quality just from these facial expression responses. And we did a study with many more types of animals and asked a lot of people to rate them. We found that they really do prefer sketches after they've been trained with a bit of human feedback in this human-in-the-loop way. So we think this is the first paper to show that a deep learning model can be improved with human social reactions. So we're pretty excited about that. But what other things are going on in creative AI? Well, one model I want to talk about with you I use for music generation. So let's get into this. So this model is basically designed to improve sequence generation. And the way you generate sequences, like text or conversations or music, is using something called a recurrent neural network. Now, the reason it's called recurrent is that this is a normal neural network, right? We just have layers, we have neurons, that's fine. In a recurrent neural network, the recurrent neurons connect back into themselves. So what happens is that not only do the output of the neuron goes to the next layer, but it goes back into itself at the next time step. So it has some sort of memory to remember the inputs that it's seen before. So if you unroll this network in time, you can see again that at each step, the neuron has access to the data that it saw from the previous step. It has access to its own state in the previous step. So you can use a network like this to learn to model sequences. So here, we're learning to model text character by character. So I put in the phrase hello, and I hope that it can predict the next character for each step of the word hello. So it turns out that if you do this, you can get a model that actually does learn something about language. So this is a model trained in the same way. You can see that it's learned to spell some words. It's maybe learned something about grammar. But what it's saying makes absolutely no sense. It's just all over the place, right? So the sequences trained in this way tend to lack structure. Like this network is talking about sisters and then sausages and submarines. I have no idea what it's saying, right? So you can't just train this type of model and get good structure. The other problem with this type of model is the sequences tend to be really boring and generic. So what the model is actually trained with is called maximum likelihood estimation. So what it's trying to do is at each step, it's trying to pick the most likely thing, the thing it's seen most often in the training data. And so it turns out if you for example, train a chatbot using all of your chat conversation histories that you have, just in case you were interested in doing that, you might get a model that ends up saying really generic, boring things. So you can see that it's just saying one-word answers, and it'll frequently say things like, I do not know. And that's just a really likely thing for it to say. Saying, I don't know, kind of makes sense no matter what the input sentence, so it's very likely. So there's a lot of problems with just training sequence models. So how can we improve them? Well, one idea is to improve them using reinforcement learning. So as I mentioned, reinforcement learning lets you optimize for a certain reward. If you have a reward function, then you can train the network to optimize for it. So for example, you can get better machine translation by rewarding the translation score. So we actually have numerical scores that we can use to say how good a piece of translation is. We can use reinforcement learning to optimize for that. So the way that people usually approach this is to first train a model on a bunch of data. So you train on a bunch of known translations. And then you would train in a second step using reinforcement learning, where your reward function is this numerical score. So this is cool, but it actually doesn't work that well. And there's a couple of reasons why. There's a couple of problems with it. The first is called catastrophic forgetting. So it turns out that no matter, like, even though neural networks are super cool, at least I think they are, they have this problem where if you train them on one task, let's say task A, and then you train them in a second step on task B, they'll basically forget everything they learned about task A. So they're basically just like Homer here. Every time he learns something new, it pushes an old thing out of his brain. He is a neural network. That's what neural networks do. So this is a problem. The second problem is that in a lot of tasks, how do you design the perfect reinforcement learning reward function? Like, if I want to generate good music, how do I write some code to tell me that this is the most beautiful piece of music? Can you do that? Because I definitely can't. I tried. It's really hard. So you often don't have the perfect RL reward function. So what you'd like to do is combine training on data with training with RL, but not forget what you learned from the data. So that's the idea behind this model. So we do this in 2 steps, just like normal. Step 1, train on a bunch of data, just like we said. Step 2, take the same model and keep training with reinforcement learning, just like normal. But what's different is that we're going to keep a fixed copy of this model and set it aside. And we're going to call this the reward RNN. So this is just a copy of the model trained on data, and it's going to help us to design a good reward function. So now, in our RL framework, the reward function becomes not only that score that I mentioned, like your machine translation score, but it actually looks at how likely the action that you took, the token that you put into the sequence, how likely that would be under the original model trained on data. So if you do something that doesn't look like anything that was seen in the training data, you're not going to get a high reward for it. So this allows you to combine learning on data and learning with RL. So turns out you can use this for music generation. You can train a model on human music and treat it as sequences of notes. And then you can try to learn how to generate music from all of this human music data that you see. But as I mentioned, you're going to get boring, unstructured songs. So that's not very good. So you can use Sequence Tutor to use RL to impose some rules of music theory on your model. So music is actually quite cool because we know that music is supposed to have a specific structure. So we can try to code this into a reward function that helps the model learn to be a little bit more structured. But again, we can't rely purely on the reward function because, trust me, it's really hard to write a reward function that describes beautiful music. It's pretty impossible. So what I settled for doing is just looking in some book that my colleague gave me that describes good music in the 18th century with some pretty simple rules. So for example, good music shouldn't excessively repeat notes, and it should resolve melodic leaps. Okay, so we can code this up into an RL reward function and try to get our model to learn it. And if we do that, it turns out that the model does effectively learn the rules that we teach it using RL. So you can see that compared to a vanilla RNN, our model has improved on these metrics that we taught it. But that doesn't really mean anything. Let's see if it actually sounds good. Okay, so here's the model that's just trained in the normal way on data. Okay, pretty boring, not a lot of structure, like I said. What happens if you train with this new approach? Okay, so this is a song that's just made up by this neural network. Let's try another one. So we see that it's improved a lot thanks to this new technique, right? It's not perfect. It sounds like a little bit like a toothpaste jingle, a commercial ad or something, right? But it's a little better, so we can see that it's improved. But what's really exciting, oh, and we know that we did a human evaluation, and yeah, humans tend to like the music from the Sequence Tutor model better, so that's nice. But what's really exciting is we think we've addressed, and at least in part, this problem of catastrophic forgetting. So what you're seeing here in this graph, on the y-axis, is the probability of the note under the original model trained on data. So this is according to the RNN that was trained on data. Now, if you train with just RL, which is this blue line that you're seeing, the model quickly forgets everything that it learned from the data. And actually, it ends up being about random with respect to the original reward RNN, or the original model trained on data. So there's basically no relationship between the model trained with RL and the model trained on data. It's forgotten everything. But if you use this sequence tutor approach, the models are able to remember more about what they learned from the data while still incorporating this reward function. So we think that that's pretty exciting. So given that this works, maybe we could use it for something else. Is there another problem we could apply this to? Well, this brings me to my third topic, using machine learning in medicine. So it turns out that one thing people want to do in medicine with machine learning is to try to do drug discovery. So what we'd like to do is we'd like to take a bunch of data about known drugs, put that into a neural network, and see if it can spit out any new things that look like new promising drugs. And the way that we do this is molecules or drugs can be encoded as this sequence of characters. So you see amphetamine here is like CCN da 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 da. So could we put these sequences into a model and ask it to give us new possible drugs? Well, we could try, but it turns out that in previous work, often it actually doesn't yield valid molecules very often. So the sequences that the model spits out, sometimes only 1% of the time will they actually correspond to a valid molecule allowed in nature. So if you're not even getting valid molecules, you're definitely not getting good drugs. But even if you are getting valid molecules, they might not have the sort of drug-like properties that you want. So it turns out that we can numerically calculate a bunch of properties of drugs, like how synthetically accessible it is, or how likely it is to work as a drug and affect the human body. So wouldn't it be cool if we could use RL to optimize for those functions to get better drugs? Well, it turns out that if you just use RL to optimize for things like drug likeness and synthetic accessibility, then your model is just going to cheat. It'll basically just end up outputting C, 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 an infinite chain of carbons, because that's the best thing to get the most drug-like molecule. So you can't just use RL. So of course, we tried using our model that combines training on data and training with RL. And it turns out that this model was able to generate significantly more valid molecules that might correspond to drugs. And the drug-like properties of those molecules were better. So that's pretty exciting. We can see some example molecules that the same technique was able to generate. And it turns out that people have actually picked this up in industry. So there's a company called Benevolent AI that is actually using this technique right now to try to generate new drugs. So that's pretty exciting. OK, so let's talk about another medical machine learning application. This is a project that I spent a lot of my early PhD on, so it's a little bit close to my heart. What we're trying to do with this project is predict people's health, stress, and happiness the next day using a bunch of data from them today. So what we'd like to be able to do is we'd like to be able to let you go about your daily life, and we get some data unobtrusively, maybe from your phone, or if you're wearing like a health sensor on your wrist. We send that data to our servers, and then we do some super cool machine learning on it. And then what we'd like to do is give you this personalized prediction about what your mood is going to be like tomorrow, given your data. So could we give you a forecast that says there's a 92% chance you're going to be stressed out tomorrow? So we think this could be really exciting because just like if you know there's a forecast that it's likely to rain tomorrow, you would take an umbrella. If you get a forecast that there's a 92% chance you're going to be stressed, you might be able to take some actions like go for a run or get some extra sleep or help yourself out. We think that the other benefit could be this long-term monitoring of people's well-being. So what we're really concerned about is if your well-being is continuously dropping, you're feeling worse and worse every day, we might be worried that you would transition into a state of being depressed. So is there some way for us to be able to automatically detect if you're about to make that transition and guide some sort of intervention to help you? So we think this could be really cool. So we spent a lot of time using this massive data set to try to train models to do this. And this data set that we have is really rich. We have people's location data, we have their physiology, we have steps from an accelerometer, we have asked them when they go to bed, when they drink caffeine, when they exercise, we look at the weather, and we even know everything they're doing with their phone. We know who they're texting, when they're turning their phone on and off. Oh my God, we know everything that these people are doing. So we should be able to do really good machine learning, right? And make really accurate predictions, right? No. Sadly, the best model that we trained using conventional machine learning techniques with no deep learning Didn't do very well. It only gets about 70% accuracy in predicting whether someone's going to feel happy or sad. But this isn't just because we're bad at doing this machine learning, I swear. This is pretty typical of what everyone's getting in the literature. Like, it's very hard to predict someone's mood. And this accuracy is just too low for people to be able to want to use that sort of system, right? So why can't we do better? Why aren't we getting more accurate in predicting people's mood? Well, I think it's because people are too different. What makes one person feel happy or sad is going to have a very different effect on someone else. So I might be perfectly happy sitting at home alone in my room coding, but that might make someone else not feel so great. So if we try to train the same generic machine learning model on both of our data, it's not going to be able to make accurate predictions. So the idea behind this project is to do personalized machine learning using a technique called multitask learning. So what we're doing here is we're treating predicting the mood of each individual person as a task, and this allows us to customize the model for each person, but still share and gain statistical strength from the data from other people to the degree that they're related. So I want to get a little bit technical here and talk about one of the models we used. We also used a deep learning technique that looks a little bit like this. But this is one of the few techniques in this paper that isn't deep learning that still works really well, so I do want to call it out. This is a hierarchical Bayesian model using a Dirichlet process prior. So what it's actually doing is that each person draws weights for their classifier from this DP prior. And what's cool about the DP prior is it actually groups people together automatically based on how similar their decision boundary is. So what that means is that if you react in the same way to the same stimulus, like you get stressed by going to a loud, crowded party, you'll get put in a group with other people that have the same sort of reactions. So you're actually clustering people over how they react to things, which we think is really cool. And so I'll talk a bit more about this later. But how well did it actually work? So here's a result of training with normal, generic machine learning, which we call single task learning, just normal machine learning. As you can see, the results are not good. We're not able to accurately predict mood, and this is pretty typical of what you see in the literature. So then we tested if just adding these multitask learning techniques works by doing multitasking over the related moods. But it turns out it's not really the technique, because that doesn't really improve it that much. But when we use multitask learning to personalize these machine learning models, we see huge performance gains, so up to 20% in some cases. And this actually allows us to reach state-of-the-art performance in predicting people's stress, happiness, and health. So we're very excited about this. We can now do this a little bit more accurately. But what's really cool is that these models that have learned these personalized decision boundaries show us some interesting insights. So we can look at the clusters of people that hierarchical Bayesian model that I mentioned earlier learned. And we can see that it clustered people into basically 3 groups. There's a cluster that's just normal people. But then there's a cluster that gets very good grades and is very conscientious and really likes routine. So these are the people that are probably like the very studious students, right? They like to study and they like to be on time. These are studious people. The second cluster is an extroverted cluster that has kind of lower physical health. And what we see is really interesting. That extroverted cluster, if they spend a bunch of time on the university campus and they text a bunch of people, especially late at night, that makes them feel good. They get less stressed when that happens. So they're texting a ton of people, that's good for them. But this other cluster, the studious cluster, reacts in the exact opposite way. So if they spend a bunch of time on campus and they have to be texting a bunch of people, that actually makes them stressed out. So it turns out that these 2 groups of people react in literally the exact opposite way to the same stimuli. So if we tried to lump them into the same generic machine learning model, we could never make accurate predictions. So this is why we think this personalized machine learning for predicting people's outcomes is really important. Okay, I have one last thing I want to talk about. It's a totally different direction. This is actually some new work that I did with DeepMind. And it's about multi-agent reinforcement learning. So the idea of the project is focusing on intrinsic motivation. So why do we need intrinsic motivation for reinforcement learning, and what is that? Well, it turns out that those successes of reinforcement learning that I mentioned earlier, like Atari and AlphaGo, the reason that they work so well is because in both of these situations, there's a really well-defined reward function that describes how they're doing at the task. So both of these things are games that you can look at the points that you get in the game. And the more points you get, the better you're doing. But how can we use RL when there's no well-defined reward function, when there's no game and there's no points? How do we learn? So the idea behind this is to use some type of intrinsic motivation, which is a reward function that the agent computes by itself that could help it learn across a number of environments. So for example, we can think about something like curiosity. If an agent is curious to explore its environment, then it might learn in many different environments, even if there are no points. Similarly, empowerment is an idea. So this is the agent tries to be able to learn to manipulate its environment. So this could cause it to learn no matter what. But if I look at this list seems a bit lacking, right? Like, are people just motivated by novelty and a drive for power? That seems a little unrealistic. I think that people are very motivated by other people. People are really good at learning socially. So, for example, if I was looking at this audience, if I was looking at you guys, and you were looking back at me like this, then I would be very strongly motivated to hurry up and get to the next slide, right? So the idea here is to try to give AI agents some form of social learning. And the way we decided to do this is to give them this intrinsic social motivation for being able to causally influence the actions of another agent. So why do we choose to do this? Firstly, we focus on actions because that means you don't have to observe another agent's reward function. And we think that's more realistic because often when we talk about multi-agent RL, we talk about things like autonomous driving, self-driving cars. And if you think about this, each car is like an agent. It's a multi-agent system where they're trying to learn to coordinate. But all of these cars are going to be trained by different companies. There's going to be a Tesla car, a Waymo car, and there's no way that those companies are going to share their secret sauce proprietary reward function with another company. So if you want agents to be able to get a social motivation from other agents, then you can't have them observing each other's reward. The second thing that we wanted to, that motivated us is we thought that when agents are cooperating to complete a task, there is going to be a high degree of influence between their actions. So if you think about like two robots cooperating to lift a box, if one robot lifts the box faster, it's going to cause the other robot to have to lift the box faster as well if they want to both be able to complete the task. So when you're cooperating, there's a high degree of influence between your actions. So could we use this to actually encourage agents to cooperate? So the way we tested this is in an Atari-like game. Sorry, we're still working in this. But the problem with these games is they're basically like multi-agent Atari, where the hard thing is achieving cooperation. So in these games, agents are running around and they're trying to collect these green apples. But it's like a tragedy of the commons game. If they eat all of the apples very quickly, then they won't grow back and they won't get any reward. So they have to coordinate with each other not to consume too many apples. In the second game, the apples won't grow unless you clean this river. So the agents have to go to the river to clean it, but while they're doing that, the other agents can basically steal all the apples and exploit them. So the hard part of these games is achieving cooperation. So they're basically like a prisoner's dilemma. They're a game-theoretic game. So each individual agent is always going to get higher reward for defecting or exploiting the other agents, but if all of the agents defect, then nobody gets any reward. They get very low reward. So this is why it's a hard game, and it turns out that a normal RL agent just can't solve it. They can't learn to cooperate. So maybe if we reward this causal influence, it can help them learn to cooperate. So how do we reward causal influence? Well, imagine you have two agents. They're just chilling out in the environment. They're looking at the state, and they're deciding how to take an action. Now, imagine that agent B can see the action of agent A, and that affects how it's going to make its decision. So agent B sees the action of agent A, and it makes a real decision. This is what it's planning to do based on agent A's action. But now, imagine that we could think about a different action that agent A could have taken. We think of a counterfactual action. What if A had done this other thing? How would that have changed B's decision about how it's going to act? So we basically ask the question, what would B do if agent A had done this other action instead? The causal influence of A on B is the degree to which B changes its mind if A changes its action, right? And so this causal influence is what we're going to use as a reward that we give to agent A. So agent A gets a reward for doing something that causes B to change its mind about what it's going to do. So does this actually work? Well, As you can see from this plot, that the red line is higher, it turns out that yes, rewarding causal influence helps the agents achieve higher collective reward, so everyone's getting higher reward, which means that they're able to learn to cooperate better. But what's actually really interesting about this is how they learn to cooperate. So in this example, the purple agent is the one trained with the influence reward. It's trained to influence others. And you can see that it's behaving a little bit differently than the other agents. The other agents continue to move around when there are no apples, but the purple agent is holding still. It actually only moves when there's an apple present. So why would it do that? Why would it only move when there's an apple in the environment? Well, it turns out that that allows it to do something really interesting, which is signal to other agents. So in this example, there's high influence between the purple agent and the yellow agent. Now, the yellow agent can only see what's in that little red box. It can't see the whole map. So you can see that there's an apple next to the purple agent that the yellow agent can't see. So when the purple agent chooses to move on the map towards the apple, this actually signals to the yellow agent that there must be an apple there that it can't see. And then that actually allows the purple agent to gain influence. And so we see this happening again in another instance where because the purple agent holds still, that signals to this pink agent that there must not be any apples, and then again allows the purple agent to gain influence. So it's really cool. The influencer basically learned to communicate about the presence of food in the environment just using its actions because of this influence reward. So influence led the agent to want to learn to communicate with each other. And we think this is a little like the bee waggle dance, how bees use their actions to signal the presence of food. So we were really excited that influence led to agents learning to communicate. And so we decided to use influence to train agents to explicitly communicate. So what we did is we let agents have a communication channel. So now they're allowed to send out a symbol on this communication channel, and the other agents will see that symbol in the next time step. And the way we train them to communicate is using this influence reward. So the agent gets reward if it says something that causes another agent to change its action. So it turns out that if you do this, again, the agents are able to learn to cooperate much better than if they don't have the influence reward, thanks to this communication. But what's really cool is that the communication protocols that they learned are actually more meaningful. So when agents are trained with this influence reward, they more often communicate about what they're doing. It has a more strong relationship with the actions they're actually taking. And there's higher mutual information between the things that one agent is saying and the things that another agent decides to do. So we think that's really exciting. It's actually learning a meaningful communication protocol thanks to this influence. But my favorite part of this whole project is actually the fact that being influenced tends to get agents higher reward. So those agents that are the most easily influenced or the best listeners tend to get the highest individual reward. So why is that? It's basically because in order to influence another agent that's trying to get its own environmental reward, trying to get its own apples, you basically have to give it some useful piece of information that will cause it to change what it's about to do because it's helpful for it to gain its own reward. So in both games, we see the significant correlation between being influenced and getting higher reward. So we think that influence is pro-social. Influence is beneficial to the listener. Okay, so in conclusion for this project, we've shown that this social influence reward can lead to better performance and cooperation in multi-agent systems. It can result in emergent communication protocols. It can be really useful for training meaningful communication protocols. And you can compute all of this within the own agent without requiring access to other agents' rewards or requiring a centralized controller. So this is a pretty significant improvement over previous work in multi-agent RL. Okay, so that's all the projects I have to talk to you about today. I'm a little bit over time, but I just want to say in summary, machine learning and deep learning are leading to major breakthroughs in a lot of areas, spanning medicine, computer vision, creative AI, reinforcement learning, and then all of these applications like voice recognition, translation, everything. So the deep learning hype train is leaving the station, and I hope that you guys are going to get on board. So thank you.
Thank you. Tenemos tiempo para una pregunta, probablemente dos. pero creo que una va a ser como... ¿Alguien quiere hacer una pregunta? ¿Pregunta acá?
Hi, Natasha. Hola, buenas. Hi, Natasha, great talk. Thank you. I have a question. What do you do? How do you handle biases from the samples? I read news about racist Twitter bots and bias against recruiting, with recruiting artificial intelligence. What do you do? How do we try to filter those, I guess, negative things to get better results from deep learning? And
That's an absolutely excellent question. So I think bias is actually the biggest scary danger of AI right now. So people talk about like Terminator stuff, that's not a real danger, but bias being encoded in these algorithms is. So if you train on historical data, like let's say that you train on historical arrest records, which are very racist, or you train on historical hiring data for tech companies, which are very sexist, and then you take a model that's going to predict who you should hire or who you should put in prison, it's going to be biased because that data is biased, and that's a real problem. But that is a burgeoning area of research. People are starting to work at ways to de-bias algorithms. So there's some really exciting stuff on like de-biasing word representations. So for example, I talked about the representations in a text model, right? It's really sad. If you look at the representation for the word man and woman and look at which careers are closest to them, like men are closest to careers like philosopher, architect, hero, like really cool stuff. But women are closest to like nurse, homemaker, dancer, like something like this. So what you can actually do with this though, there's a really cool algorithm, is you can actually make the representations, you can train the model so that those representations of gender are perpendicular. They basically have no relationship with any of the career words. And so you can like automatically de-bias the model. And that's really cool because people would say, oh, well, what if bias is part of the world? What if you de-bias it and the model doesn't actually perform as well? Turns out, no. The model still performs excellently on all of the analogy tasks. Like, there's no loss in performance from taking that bias out. So there's some really promising research in that direction.
Fuerte aplauso para Natasha.